everyone, and welcome to another episode of the Data Science Decoded podcast. I hope you're well and everything is great. And I'm here with Liron and Mike. And how are you guys?
We're good. How are you?
Not bad, not bad. I think it is the first episode after 1.5 months, during which we have not recorded. Maybe I can partially explain it by August. Many folks were on vacation, but still, I can promise we will try to record at least every 2 weeks. I can't guarantee we'll do it every week, but at least every 2 weeks we will try. We'll do our best to do it.
Yeah,
Hello.
I am on board, and I guess we all had vacation, summer. I was abroad, and then I didn't have reception. So yeah, that's life. And how are you, Liron?
I'm good. I'm working a lot, so for me it's not that hard right now. But August is always challenging.
Yeah, so now we are in September, and indeed it was a long break, and I'm happy to be back. And yeah, as everything in life, we know it, 80% is showing up. So 80% of the reward in our today's chapter paper, I mean. And yeah, so we're gonna continue showing up and doing our best. So today we're gonna go over a paper by Richard Bellman, Markovian Decision Process. That's the title. And to our listeners, you probably remember we had, I think, like 8-9 months ago, a paper also by Bellman about dynamic programming, and it was our second most watched episode after Fisher. So apparently that's an interesting topic, dynamic programming, or at least not enough addressed by other people. So we are here to do it. And in it, we went over what's dynamic programming, and we mentioned a little bit about Markovian Decision Process, or MDP, but we didn't go deeply in it. So this is the chapter today. And this paper is from 1957, so it's 3 years after the paper of dynamic programming. And just a little bit background about Bellman. So he did his PhD in math, so he's a mathematician, but a lot of his work was done in the Second World War II. He was part of Los Alamos project, so he worked with a lot of physicists, probably modeling various physical properties or simulations, and that's why maybe he needed dynamic programming. And again, that's my speculation. And as I told you also in the previous episode on the topic, later in his career, he went more into like biology stuff. So that's interesting. I'm curious to hear about from you, Liron, if you heard about Bellman while doing other stuff like in reinforcement learning.
Sure. So Bellman is the cornerstone of reinforcement learning, right? Everything we do in reinforcement learning is an application of dynamic programming. And the principle of dynamic programming is the reason we can have value functions or we can have policies. So that's like the most seminal work maybe on what reinforcement learning is. It's before the learning is what's the point of like doing something with a process where you're trying to optimize reward over a process. That's always dynamic programming. So very seminal, everything relies on that. MDP is actually very interesting, what we're going to be talking about today, because a lot of academic work has been done on that, and all the basics, all the basic stuff of reinforcement learning, everything we had before deep learning up until Q learning, I think, really
Tell us
relies
the
on
years
that.
when Q learning was introduced.
I don't remember by heart.
Probably in the 70s, right?
I'm not sure if Q learning was around in the 70s, but it it's possible. I mean, Q-learning is you're just learning on a table, right? You have a table of discrete states. So it could have been done in the 17s, though I doubt it was useful. But yeah, everything we do in reinforcement learning developed from that basic.
Cool.
Yeah, and by the way,
Mike?
I'd like to add something. In today's world, in which the most popular words are agents and LLMs, we are training our LLMs with RLHF, which is reinforcement learning with human feedback, and we have RLVR, reinforcement learning with verifiable rewards, and I think all this stuff was not exist without Richard Bellman, which, as Liron mentioned, laid the foundation of all we know today as reinforcement learning. So if you like your agents, if you like your LLMs, please try to understand this episode. We will do our best to explain it.
Cool. Thank you for that, guys. And yeah, I totally on board, and that's why we're reviewing those papers, because we slowly try to move and then hopefully introduce reinforcement learning in future episodes. I just want to give the viewers or listeners that, let's say, stumbled upon this topic for the first time some intuition. So let's say you try to optimize some process and you can make decisions at each step. So I think the most trivial way of tackling this problem is just at every step do like a greedy algorithm. I'm gonna do whatever give me the most reward at this moment, right? So let's say if I'm playing chess, I would just move the piece that will make the most damage or eat the piece with the most value of the other side. But that doesn't mean it's the most optimal policy to win the whole game of chess, right? And that's, in a sense, the motivation of dynamic programming and Markovian decision process is that at each step I take what gives me a lot of reward, but I also take into account future reward or outcome of my decision at this step, right? And then maybe this combination of those two is much more optimal.
Let me look at it from
you agree with the way I formalized it?
Yes, it's correct. Let me look at it from a different angle. So essentially what dynamic programming tells us is, well, you are right. If you're just greedy, you will not win in the long run, right? So if I'm trying to optimize one step ahead, I may go out tonight and have a beer with both of you and skip recording, and we'll just drink beers until we all pass out and forget to come back home. That's very optimal for one step ahead. But none of us are doing that. We are recording a podcast right now, and then we're, I don't know, working out, spending time with our families and those kind of things. Because, well, sometimes that's the thing we most want to do at that moment, but other times we do that because that's more optimal in the long term. So we are not making decisions based on just a greedy approach. But in a sense, we are, because we are choosing something that makes us feel good that we do that. And essentially what Bellman told us is that for every problem, there exists some sort of a function. You can call it the overall cost or overall reward, that you should be greedy with respect to that. We don't know what it is. It's not just the instantaneous reward, but it's the total reward we will get. So one way to think about it is the sum of rewards we will get from that point on if we choose that path. Okay? Or the maximal sum of rewards that we can get. And of course, there are two caveats you put into that in modern reinforcement learning. Well, if your process is stochastic, then you cannot know the rewards. So it's the maximal expected reward. And the order is important here. It's maximal expected, not expected maximal. And the other part is if you want to hedge your bets to an extent or just make the numerical convergence easier, then you don't look at the total sum of rewards, you look at a discounted sum of rewards. So rewards you get first have some priority over rewards that come later. So
it's weighted.
It's weighted by the distance. How far is it into the future? You have some sort of
like weighted decay in
exactly.
optimization.
Yeah, exactly. It's exactly weighted decay.
Thank you for that, because it dovetails exactly into the first equation of the paper, right? So I'll just read it for our listeners. So he says the purpose of this paper is to discuss the asymptotic behavior of the sequence fn of I, where I is between 1 till m, and n between 1 till something unspecified, generated by the nonlinear recurrence relation. And here he says like the total value, what we call value function, or here it's like fn of I, where I is the state I'm in at the moment, is the maximum. So I'm trying to, I'm incorrect?
Yes, the way I read this equation, it's simply a vector valued function. So I is the number of element on the vector. So f is a vector. F, the first element of the vector is fn1, and n is actually the time step.
Okay, so the state is a capital N. That's right. The state I'm in the moment is f of n is capital N.
Yes,
I think because then it's dependent on the previous step on n minus 1.
Yeah, so this is from the 50s, so vector notations were not as common, so he's actually using a scalar notation, which is making it harder for us to read today, but would be more common. So if you actually write out the matrices, you would write them out like this. So
so just to reiterate, the current state, I'm trying to maximize, right, two things, which is the reward I get of doing something now, which is in his definition bi of q. Q is like the policy or the action I take. And then the effect that comes from like the previous step that I took, right? That's the combination of two things, and I'm trying to maximize them.
Yeah, so you have a part which depends on the former value of f. So you can think about it as a matrix A multiplying f at n minus 1. And then there is the part which is independent of f, which is just b of q. And both a and b are functions of q, which we maximize over. So we maximize over
b
q.
Is the reward
Is an
I
immediate
get
reward
at this step.
So Leron, I have a small question to you. It's something that I'm not, I don't fully understand. So do we assume that n is a constant, and then for constant n we just define a function for maximal number of steps n for a given step number I, or I'm wrong about it?
I'm not sure I fully get the notation here. So I think he's using n for two different things, but the way I read his equations, he's saying, basically, I've shown you before that if I do dynamic programming, I get a reward to go function that I can greedily optimize over, and that's okay, right? So I can greedily optimize over this value function or Q function that I chose, and that's actually okay. That's optimal, right? Yeah. So now he's saying, okay, let's assume I have this function I can optimize over, right? So I'm always choosing the maximum over Q in a greedy manner here. And then what is this function of Q? Well, it's a linear function of f. That's all he's saying here. So it could be a very complicated function of Q, but it's linear in f. So I'm summing over the history of f's. So there's a constant term b, which is still a function of Q, just independent of f. And then there's a function of f in different time steps, right? So
okay, it sounds reasonable, yeah, but notation, the notation is not very
Yes.
It's not very clear. It's a bit. Yeah, I see some ambiguity here.
Yes, it's hard to read. Also, in this particular equation, it's very hard. Why is this so far away? I was in the example on the other computer. I cannot really read what is fn. No, it's fn minus 1. So it's
Yeah, it's
just the previous step.
step.
So
Yeah.
it's one
Exactly,
previous step.
step.
Yes.
So that's the idea of a Markovian process, right? Because the current state is only dependent on the previous one.
Yeah.
Yeah, well, it could be dependent on n previous measurements, but since it's a vectored valued function, you can always fold that into a vector and look
Yeah.
one vector backwards.
By the way, this is exactly what we are doing while training LLMs, because we are building our context all the time. You know, for token number n, the context is n minus 1 previous tokens, and for tokens number n plus 1, we have n last tokens as a context. So it is exactly what we do there.
Is it because an LLM doesn't look at a limited set of steps backwards? An RNN is doing that. It has a single vector that you're always looking one vector back when you're generating the new prediction and the new vector. But for an LLM, it's actually looking at all the history it can see.
Yeah, but what is all the history it sees? It sees all the previous tokens you already generated, right?
Yes, but
so your state is always all your previous tokens. Okay.
Yeah,
and
but
this is exactly what I said. Maybe I just formulated it wrong. It's wrong.
Well, maybe I'm not getting it, but I think this process you're describing is not Markovian, because Markovian is looking at most n step backwards. There has to be a finite amount of steps where within that scope you can say that predicts the future.
Okay, in a strict sense, you are right. Yeah, I understand your point. Okay.
So,
so let's continue.
Yeah, let's continue. Okay.
So the main work in the paper, so now there's like six sections where he shows that, well, although this problem is not linear because we're trying to take a maximum of something, and the maximum is a nonlinear operator, under some conditions it could become like quasi-linear, as it says here. Although these equations are nonlinear, they possess certain quasi-linear properties which permit a more thorough discussion than might be imagined upon first glance. So he's just trying to show, okay, don't worry, it's not as complicated given some assumptions, and maybe we can make it like quasi-linear. And again, this is 57. So computationally, it was difficult to solve those problems, and analytically, you cannot solve this, right? So what they had to do is make assumptions and approximations, right, guys?
Well, basically, you can solve it for some very degenerate cases where all these transition matrices are very small, have some very convenient properties like bidiagonal or maybe something like that. But in general, it can be solved.
So it can be solved in terms that you can formulate it as the Bellman equation or the Hamilton-Jacobi-Bellman equation, depending on the case. And then you say, okay, if you solve this partial differential equation, then you solve the problem optimally. The problem is we don't have a good way of solving partial differential equations. And essentially, that's what we do in reinforcement learning. We are approximating the solution of the Hamilton-Jacobi-Bellman equation or the Bellman equation using a deep learning algorithm, using a neural network, right? That's all we do.
Yeah.
So you're saying, well, if you have some action space which could be continuous or discrete here, it doesn't matter, and the process is Markovian and linear in the state, in the F, then we can discuss it. Then we can do some math around it.
Okay.
Yeah, exactly. And Mike, you said the degenerate, so I got triggered, but it's okay because we're talking about math, and you weren't applying something about me. So anyways, we won't go over the assumptions and the derivations that he's doing here, but equation number 2 is given the continuous Bellman equation instead of the sequential one. And
Leron, by the way, is it somehow related to Volterra equations, or it is something different?
Well, if I recall correctly, Volterra equation refers to the population of specimens in the population of different specimens over time. So
yeah,
you,
but okay.
so you
Maybe,
could
maybe.
you could
Okay.
refer to Volterra's equation as an underlying process, and it would be Markovian, but I'm not sure you will get this kind of MDP over it, because
Okay.
the value function, it's not the value function,
Okay.
the reward to go function will not necessarily have this quasi-linear structure.
Okay, I see. I need to recover it from my memory, to ask some LLM about.
But you could look at it as related to a bandits problem.
Yeah.
Oh, that will be a future episode. I'm talking about just the bandits formulation.
Yeah, multi-armed.
But I wanna focus now on the section number 7. So again, all the 6 first sections, he gives some assumptions and approximations in order to, again, somehow solve this equation in a way that makes sense and is useful. At the end, he is a mathematician, but he's trying to give something useful for us, or for physicists and engineers. So section number 7 is an example. So let's go over the example, and hopefully it will give us more motivation and intuition. So he says, let us now briefly describe a dynamic programming process which gives rise to recurrence relations of the type considered above. Okay, cool. He says, consider a machine which is used repeatedly to produce a certain type of an item. At each stage, there is a probability that the machine produces a perfect item, a probability that it produces a defective item, and a probability that the machine breaks down and requires repair. These probabilities depend upon the age of the machine. Okay, so at each step, there's 3 outcomes, and he says the probabilities depend on the age of the machine. So when I'm reading that, I'm thinking, oh, that's not Markovian, because the process should have history. But again, he's going to solve it, right? But when I read it, that's what I thought. And he says, examine the matter in more detail. Let us suppose that there are k different sources of failure within the machine, leading to either defective items or breaking down of the machine, or both. And he defined 2 probabilities. Pi of n, so the probability that the machine breaks down due to failure at the ith source after it has successfully produced n items. And Qi of n, probability that the detective item will be produced due to hidden failure at the ith source after n items have been successfully produced. Okay, we're cool now with the definitions? Nice. So he continues, at any particular stage, we face the problem of deciding whether to examine the machine for possible failure at one of the sources of trouble, or to wait until a defective item is produced. In addition, if a defective item is produced, there is the question of whether we should repair the machine insofar as the immediate source of failure is concerned, whether we should, in addition, examine other potential sources of failure, or whether we should automatically provide new parts at various sources of failure without preliminary inspection. So I'm getting a little bit lost. So the idea here, I have some kind of a machine with some parts. I guess how many parts or sources? You call it sources.
K different sources of failure.
So you can think about the vector we have, F, as different potential failures, right? Zeros or ones, where if it's 0, this part performs okay, and if it's 1, then this part failed. There's some sort of failures there which could be hidden.
Okay. And the idea, he says, the decisions, so either at each step, should we fix, should we do nothing, those decisions, of course, will be dependent upon the cost incurred in carrying out these operations. The cost due to defective parts and the cost due to breakdown of the machine. Because if I have one fix, at some point it would break. So now I'm trying to like optimize some kind of total cost in the long run, or let's say minimize.
So maybe an easier analogy for those of us doing software for a living is looking at cybersecurity. You can have a lot of cybersecurity issues. You can have a lot of potentials for issues, right? Or a lot of vulnerabilities. And you cannot just always be fixing all of them, right? So you can let production run, hope nothing happens right now, or you can look at the different sources of problems and you can say either there's not going to be any data corruption, or there is going to be some data corruption, or it's going to break production, right? So we can say, okay, those causes, we cannot stop and fix all of them or stop and inspect all of them all the time. That's going to be very expensive. But if we stop and check for one, we say, okay, there was a problem here, so we're going to check it, we're going to close this gap. Maybe we should also inspect other problems while we're doing that. Does that make some sense?
I'm trying to understand. So, does it mean that if you have a failure of type I, does it mean that necessarily the next stage, the next item we're gonna produce will be broken? So, or we can have some problem, some failure of type I or I+1 or whatever, and we still can keep producing valid items.
We could. So some failures could just stop the machine altogether. Some failures could just produce a failed item. Now it's a matter of formulation, right? If you're under deterministic formulation, it would necessarily either break the machine or produce faulty items. But if you're willing to take a stochastic formulation, it could just have a probability of either.
Okay.
So given any combination of failures, you could have the probability of generating a faulty item or having the machine break down.
Okay, so there is another state which is machine broke down, right?
So in this case,
I don't see it here.
It's hidden here, because what you have here, the F, the state here, is the state of the solution of the Hamilton-Jacobi-Bellman equation, or the Jacobi equation actually is more common. So the state that you see here is the state of the optimal solution, not the state of the actual machine.
Yeah, exactly. Because here we're gonna define it now, so that's great point.
Okay.
The state of the system at any time can be characterized by a set of numbers between n1 to nk, specifying the number of items n produced since the IF source of trouble was examined.
Oh, okay. It's a very specific example.
Yeah, it's very specific, and here, at least for me, he has the history part, right? So if the machine wasn't fixed for a long time, so n is going to be larger. So that's how he takes the history that I would want the system to have and put it into Markovian sense.
It's amazing, actually. You can see how much of a genius he is here, because for me, formulating that in an example which is deterministic and would make sense for most engineers is like so hard to formulate such a complex mathematical case into something. I'd have to think about it long and hard. Maybe I could come up with something. And then he has something super simple just here, like there wasn't this failure for this many time steps. Simple, deterministic, and then, Mike, brilliant.
What you said is the problem is then to determine the inspection and replacement policy, which minimizes the expected unit cost of production. So the actual function we look in here is not the machine itself. It's the cost, the total cost of doing all of those replacement and checks, etc. That's what we're trying to minimize. So he says, to treat this problem, we begin with the problem of determining the policy which minimizes the expected cost of producing capital N items. Define the sequence of functions Fn, which is a function of the vector that we described, N1 to Nk, which is the expected cost of producing N items using an optimal inspection and replacement policy, starting in some state between N1 and Nk. And then he says, following this definition, it follows that the effect of any decision to produce without inspection or repair, to inspect with a passive replacement, or to replace is to transform the system from its present state into another state. Assume that only a finite number of states are permissible and enumerate them in some order between I1 to M. Any particular decision designated by Q, so Q is like a decision at each state, leads to a recurrence relation that we talked about.
Right, that actually explains why he wrote the equation in scalar form in the beginning, because each component of the vector is a different decision, right? So for each component, he decides, do I need to inspect that or repair that, or just let it keep running? So the decision is actually independent for the different component. He's maximizing over each one of them individually, and that's why the maximization is being done in a scalar formulation.
Okay. So let me see if I understand.
I'm not sure I understand, right? This is like very complicated notation I'm not used to and very brilliant. So I hope I get this correctly.
The state of a system at any time can be characterized by a set of numbers. So yeah, I'm not sure I understand, because in my view, maybe it's like Mike's. Okay, I have a machine with some parts, and each time, so let's say every day, so I have some time aspect, I need to decide if there are like different parts of the system, if I should inspect or fix or repair any of them. So that's the vector, because I have a lot of parts. For each part, I can decide what to do. So
right,
that's
for
like
each
a vector.
Part.
Yeah, yes. Let's say per day, I'm gonna look at this vector.
So
but then he has the number of days since last repair, which is not something that I can use. So that's why I'm confused.
I don't think M is the number of days. I think M is the number of states. And
no, lowercase n is the number of lowercase n. I is the number of days since the ith part has been repaired.
Yeah, that's where he defined it somewhere.
Yeah. Down. Go a little bit down here. The state of the system, second paragraph. Number of items produced.
It's not talking about days.
Since the I source items, you're right, it's items. I'm assuming discrete time is uniform, but you are absolutely right. It's not a uniform discrete time, it's number of items produced.
So
so each time.
Okay. Go ahead.
So each component of the vector is how many items were produced since it was last repaired. Okay, so suppose I have, I don't know, something mechanical, right? Like, I don't know, a microwave. Everyone has one at home. So we don't usually have to fix the microwave, but let's imagine we do. So we have kind of the electromagnetic emitter, right, which is generating the heat, and we have the power adapter, which is adapting power from the socket to the device, and we have, I don't know, the keys that we're pressing, right, to use.
Yeah.
And then, like, each one of them has heated food n times without breaking. Now, if we were to look at fixing each of them individually, like they probably did in the 50s and did have microwaves, but so like if the thing that emits the electromagnetic wave breaks down, you only replace that. So how many times will it work until you have to replace it? Well, there's a finite amount. There's some policies there. You say, okay, well, if it has produced, now it worked for 100 heat ups, that's when you replace it, right? It's probably the best time to replace it before the microwave breaks down. Well, it's easier to see on the bottom, right? The bottom, we know it will break at some point.
Yeah, so now you say I'm trying to minimize the cost of repairing the whole microwave. Now I have some kind of vector pair part of the microwave, and like how many days since the last repair, or not
Yes.
days, maybe how many
Heat
checks, yeah, or something.
Yes.
Okay.
There's a slightly more complicated reward here, because it's saying, well, you can have two types of problems, right? One is that you produce a faulty item, so the food just doesn't warm up well. And the other is you can have the machine malfunction, so the whole microwave just stops working. Okay, so you can have either of the two, and then your reward or your loss is dependent on the type of error you got.
Yeah, I think for me, this is exactly what is absent here. Okay, all this cost, all this repair, all this malfunction of this, this machine has some cost. Okay, and this cost does not explicitly appear in these formulas, and it should, because we want to minimize the cost or maximize number of items. I think I'm not sure I'm fully understand this example, because you have a lot of too many unknowns here.
Yeah, he does mention it somewhere, right?
Yeah, I am with Mike, because here we define like P and Q, but then we're not using them. Like this Q here, it's not the Q that was defined, right? This Q is probability.
Yeah.
No, it's a bold Q, and this is not bold Q. This is regular.
Yeah, so, and we don't use P at all. So I feel like we know this equation because this is the Bellman equation, but I feel like the example is not mapped, at least to me, in a way that is intuitive.
Yeah.
But it's okay. We can say, okay, he gave an example that is confusing, or at least he didn't explain it well, maybe assuming people would, understand it straight away.
Yeah, he didn't give those kind of details in the example. Well, in the 50s, the kind of people that would read those papers would also be able to solve integrals in their heads. So, maybe we're not the crowd for that. None of them would be coding all day like Python does 90% of the work for me. I just write one line of code and everything runs. But yeah, I cannot do it in my head right now, converting it into a closed form. But even if I could, then I would have to translate it to the solution of the dynamic programming language. And I think all he's saying here is you could do that. You don't have to really understand the details. Just if you can do that, and there's a different cost to the machine failing altogether and a different cost to just one item being produced faulty. So you can kind of work out the numbers. If you work on it, I just want you to understand that this is the kind of problems I'm talking about.
I just want to add, I think the idea, at least that what I was thought he would try to say. So let's say we understood the example, because if you think about this machine, let's say even the microwave, so at each step, it would be hard for you to say, it's a Markovian process, right? Because I would tell you, no, of course I need to know the whole history of each part. But I think the trick, or at least the thing that you said that is smart, he somehow encoded the history, which is how many steps happened before last change, into a state vector. And then at each time you come to do the inspection, you take the current reward plus this state vector with the history encoded in it. So in a sense, he took a problem that is not Markovian and made it Markovian. So I think that's the idea behind this example, as far as I get the motivation.
Yeah, I tend to agree. I think your state is merely one number. You just know that this is part survived for 100 steps or 50 steps, and this is, this number is the state actually for each type of fail source for me. But
So
maybe we all wrong here.
these numbers represent the cost, right? So how much would we pay for a failure? So on the I step, we would pay for, if there's failure in this component, this is equation 3 I'm looking at, right? Or equation 2. So if there's failure in one of the components of F, right, on the jth component of F, we will pay for it in the ith component of the loss based on Aij, right? So those are the different ways it would affect it. And then what happens is, if we decide to replace a part, essentially repair the machine, repair the ith part, then the history, the number of items produced since it was repaired, zeroes out, right?
Yeah.
So that's the maximization over or minimization in this case over Q. So we choose to minimize such that this overall component of the vector is minimized.
Yeah.
Okay, interesting. And I wanna, because we're finished the paper, and I wanna just give the listeners something to take home. So let's say our next chapter will be bandits. How does this paper relates to bandits, if at all? Maybe I'm wrong. So Mike, what do you think?
I think the next chapter should be about Q learning, because I think
Okay.
the most smooth continuation, most smooth analytic continuation of analytic. I don't remember something in complex analysis. But I'm talking about the most smooth continuation of this part will be Q learning, and
Okay.
because maybe after Q learning we can talk about bandits, because they are really related. For me, at least for me.
I don't really care about the order, but to answer the question, so the state of a bandit is just the expected reward of a machine in the bandit problem, right? So, and what I'm minimizing is I'm choosing which machine to measure, and I'm essentially maximizing my expected reward. It's very hard to reach a closed formulation for a bandit's problem, but you have to make some assumptions. But essentially we will be applying that, since if it's constant, right, the reward of a machine is constant, so it is Markovian.
By the way, Daniel, I think because in the bandit problem we have some inherent random component, because I can think about any bandit if there are not some random stuff in there, and here we have some let's say not very random stuff. So at least for me, these two are quite weakly connected, and that's why I suggest talking about maybe Q learning.
Well, both would work.
I don't insist.
Remember, this is the optimization of the overall reward.
Yeah.
So the optimization of the overall reward is deterministic even for stochastic processes.
Yeah.
But a bandit has to be stochastic, of course, because if there's no stochasticity, you get the reward from a machine once, and you know that this is the reward it will give you. Then you just try every machine once and you're done. You just go to the one with the highest reward.
Yeah. No, but in stochastic case, are we talking about expected reward?
Yes. Well, expected statistic of the reward, depending on the statistic you're trying to optimize.
Yeah. Mike, we touched upon that in the original paper. He had something about stochastic Bellman equation.
Okay.
Or at least with noise. He talked a little bit about what happens when there's noise.
To make what I said accurate, I mean, there's no sense in saying the expected value of a statistic. Some statistic, it could be the expectation of some function, which is usually what we refer to as a statistic in this sense.
Yeah.
Sorry for being all mathy.
Oh, it's okay. It's okay. We need to be precise, because if we won't be precise, who will be?
Well, isn't that what professors are for?
Soon they'll be unemployed. No.
Well,
Not
AI
because of
employed.
LLM, because of funding.
Yeah.
Well, I like the term AI employed.
Yeah, employed.
Okay, cool. So thank you very much. I had fun, and I'm happy that we're back, and hopefully we can continue this
And sustain the tempo. Maybe
yeah.
maybe we will even try to do
with a constant frequency.
Yes.
Yeah.
Okay, so thank you everyone, and see you next time.
Bye.